Last video we just talked about the constant velocity motion. Now we are going to talk about the accelerated motions, and the function for u would be like this. Time it will be changing, and with the slope of theta is equal to the acceleration, and for acceleration will be constant throughout the time. Acceleration with time it will be constant. So in order to actually code this type of problem, you need to understand first of all the equation of motions. V is equal to u plus at, and x is equal to ut plus half of at square. Usual way of coding is like using delta t, constant delta t, as 1 second or 1 unit, whatever unit it might be, 0.1, 0.2, whatever it can be. So there are two ways of coding this. One is using simple t range or t range from t initial to t final. In here xyz state during different time won't be saved, and the other ways of doing this is by actually coding it for delta t of unit time. So u at 2 second would be like u at 1 second plus a t. Since t is equal to delta t is equal to 1 second, acceleration is constant as a, so u at 2 would be equivalent to u at 1 plus a time is delta t, that I would keep delta t. Similarly, the position vector of a particle at different points would be given by x at second time interval. Second iteration would be x at first interval plus u at first interval delta t plus half of acceleration, that's constant, delta t ka whole square. So this is the way we are going to save the state of the function at different points, x2 or x state at different state, y state and z state. We'll be creating a function called as state for this type of method. So first we'll be talking about simple code, then this state one. Okay, let's dive into the code. Okay, let's code for accelerated motion. In the previous video, we just did a constant motion and just sinusoidal motion as well. There were two particles. At the end we did for two particles. Now in this new video, we're going to talk about the accelerated motion. So okay, there were two types of motion. I told you there are two methods. One is like using the range of time, and another is the constant time, delta t, constant delta t. First of all, we will be coding for time range accelerated motion. So we would need up to this part, same thing. Time will be same, t, we don't need time period this time, sine wave are not needed, 0 is enough. Okay, only one particle we need, we don't need to code for two particles. So initial state we will keep it at 0, 0, 0. Okay, initialize it, nice, x, y, z, and limit, I think limit start should be, we will keep at 0, 1, this up to 50 or 100, whatever you like. So okay, this is 0, 0, 0. So for the first thing, we are going to code for time range t, and we will need equation as x is equal to ut plus half of at square. So x is equal to u into t initial time plus half of a into a t ka whole square. Initial time is t1. This is t1 is 0.0, the first one. We don't need this thing, and in y and z axis it's not changing at all. Okay, this is it. Yeah, and we're going to initialize the u. Initial u is equal to 0. You can change it later on. Acceleration 1 meter per second. We'll name it as a good code given and make another section as code. Let's code it out. Okay, so we need a go for the time range. For initial state has already been plotted and saved. For I is equal to 2, so we are going to start from 2, not from the initial state. The second state to length of time. X would be, yeah, I'm going to call it out x, y, z. Okay, y won't be changing, and z axis or z coordinate will also not be changing, and x will be changing according to this formula. In here, we're going to keep u won't be changing. Yeah, it will be changing for every time second is increasing, but in this method u is kept same as 0. It doesn't have to change because time is changing, 1 2 3 whatever it is, time is changing, so we don't have to do like that. In the next method we have to change the u as well. In here we don't really need to change u, and we can copy paste this part from here, and we don't need index it. You can index it and save all the states, but we don't need it for now. Actually, we don't need those two things. We can delete it. Just a generalized thing, we're gonna keep it there. This thing, if you need to just create a video file, then you need these get frame. Okay, let's see if it works out. Play it out. Okay, good. It's moving up to 50. Okay, this is it. This is for the first method pretty much, and if you want to change the initial velocity 10, it will go beyond, I think, this range. Yep, it will go beyond range and stop at 150. We can change the acceleration as well. No hard and fast rule in that. Now we're going to create the second create a second code for the second method. Second method was like constant time as dt, acceleration. Oh my goodness. Okay, I just named it. This thing it doesn't look like that. Okay, in here we're going to keep dt as same, so we don't need time range. T initial we can keep it as 0. T final we can keep it as 10 seconds. Ti is equal to 0. And yeah, dt, most important dt. For now we are going to keep it 1 second, later on we will change it to 0.1 or whatever unit we want. Acceleration u, and in here you have to remember u is not 0, u is actually a semicolon to final velocity. Oh yeah, u is actually u is not 0 and velocity 0. Final velocity is changing. So what I mean by that is in here u is gonna change, u is going to u into dt, and not u dt, u v is going to u plus 80. For next iteration u would be v of the first iteration. Acceleration into dt, and we have to change every time dt at d is not used, dt is like near time. Okay, and yes, x, I just told you initially it is x u dt plus, okay, for every delta t initial state has been ended up. Okay, I think in here I have to change it. dt, it's initial, dt is going to, oh my goodness, this time we don't actually use this and go for x is equal to 0 initial state. Yep. Okay, let's see if it will work. Ti, yeah, and for how many lengths? We're not going for length because we are not using t this time, so we're gonna create a variable called count, and we won't use this now. We're just gonna use while count is how many times this iteration should go on, less than or equivalent to while count is less than or equivalent to t. Okay, how many counts should there be? Tf minus ti time t from 10 divided by dt. This number of times it should go on if we actually play it out. Yep, number of times. So how much should you run it out first? Is my laptop hanging? What's happening? Okay, yes. Okay, yeah, alternate. I can actually close it up. So I was What's happening? TF is changing every time. That's why it's like that. Yep, I knew it's gonna happen like that. Ti 10 minus 10 0 doesn't matter. So you just name, because it's changing every iteration, TF is changing there. It should not change at all. This one, let's see if it works. It did work. Okay, for 0.1. Okay, 0.11. We'll just keeps like that. Yep, good. Okay, this is it. We just created a function state. This is the updated state. This is the initial state. You can actually index it. Okay, to save, you can actually make a variable like this, x variable, to save the state. It's equal to x, and you can save the state and velocity also. X is equal to array is much positive. Okay, I haven't defined I just need to define count. Array count. Now it. This way your state is saved here. You can see it. Every state. Wait a second. Count is not increasing. Yeah, open the wrong one. 0.00 up to 50. Every state is saved here. You can do it for velocity also. So I think this was it for the accelerated motion. So much so 0.5. We can keep it a little bit slower. Yep, this is it for accelerated motion. In the next video, we will be just going for random motion. We won't be giving some acceleration or velocity to the particle for every state that I made here. We'll be giving a random motion to the particle. And also we are going to keep bounds on the space. We're not going to let it go beyond the boundary we have just mentioned. Okay, in the next video we will do that, like what I mean. If I give something like 10, it's going to go beyond this one, and we won't be able to see where it went. Either you have to just increase the bounds or automatically, or we can create a bound, and we just have to just do a random motion of the particle. So that is it for this video. Thank you.